Okay, this is review video number 8 on static electricity. Now, one of the first things you need to know about static electricity is this letter right here. Oops, let's not do it with that color, let's do it with this one. Q. Okay? Q is the charge on an object. And a lot of times you'll see, one E, or one elementary charge. And that's the charge on a proton or electron. They're equal in magnitude but opposite in sign. And one elementary charge equals 1.6 times 10 to the negative 19th coulombs. Coulombs are our unit of charge. Okay? This is not a unit of charge. That is not a value of charge. That's a shortcut to tell us that we need to change that into 1.6 times 10 to the negative 19th. Okay? A lot of times we'll say in the question, one electron or two electrons. That's your cue that you know the charge. They might not come right out and say it, but you need to know it. Now, the only experiment that you kind of might need to know that they've ever slightly asked about it is Millikan's. Okay? And Millikan's oil drop. Now, he's the one that had those two charged parallel plates, and he was looking through a microscope at these, here's his eye right here. And he was looking at little drops of oil that were ionized, and he was adjusting the electric field between the plates until those little drops of oil floated. And once those little drops of oil floated, he was then able to figure out their mass and then figure out their charge to mass ratio. So he was the first one that came up with the idea of the essential charge per unit mass, and that the charge on an electron is the smallest possible. So every charge must be a multiple of 1e. So it must be a multiple of 1.6 times 10 to the negative 19th. So 1.7 times 10 to the negative 19th coulombs cannot exist. You cannot have a partial electron. It must be a multiple of that. Now, much like anything else, charge is conserved as well. So whatever charge is lost by an object has to be gained by something else. Okay? So if you have a balloon that you rub on your hair, and your hair loses, 4 electrons, then that means that the balloon must have gained 4 electrons. Okay? You can't misplace electrons. They have to go somewhere. Now, when we talk about charged objects, now anything that's like, so a positive and a positive, or a negative and a negative, they repel. That's an easy one. But things that attract, okay, we all know that opposites attract, so a positive and a negative will attract, but also a positive and a neutral, or a negative and a neutral. Okay. Neutral things are always attracted. I showed you, I'll explain it again here. Just like if you rub a balloon, so that balloon has all sorts of negative charges on it, and you bring it near a neutral wall. Okay? What happens when you do that is that these electrons here get repelled, so they move backwards. Now, as those electrons move backwards, you're left with just the positive charges at the front of the wall. The electron is now back further in the wall. So that makes that wall surface positively charged briefly. As soon as you move that balloon away, then those electrons come back home and they make that object neutral again. So neutral objects are attracted to any charged object. Excuse me. Now, there's different ways in which objects can gain charges. Okay? There's charging by contact, which is conduction. So let's say that we have a charged metal sphere, conducting sphere, and it comes in contact with a neutral sphere. Okay? Let's put another charge on there. So as these two come in contact, things in nature want to balance out their charge, just naturally. Okay, so this would be the before, and then after they come in contact, it would look like this. Okay, two positive charges on that one, and then two positive charges on this one. Now, one of the ways that we can figure out what the charge on each of these would be is if we take this total charge, let's say we know that this is, and this is not correct, but let's say this is 4 coulombs before they touch. In order to find out the final charge on each of them, we just simply find the average. So divide those by 2. Sometimes they'll then throw in a third sphere, and then they'll say that, if they label these A, B, and C, A comes into contact with B, and then B comes into contact with C, which means that our final charges are then going to be A with 2, but then after B comes in contact with C, then they split each other in half. So each one, B and C, has 1 charge. So that's conduction, charging by contact. Induction is a little bit different. Okay? Excuse me. Let's say that we have a neutral object here. And we have a positively charged object here. And remember that only electrons can move. Okay? Protons can't move. Only the electrons move. So if we go back to this one, it's not that these electrons are moving over. It's simply that this balloon right here is losing electrons. When it loses those electrons, that cancels out 2 of these charges, and now we're left with the deficiency of electrons in this balloon, which makes it positively charged. The protons are never moving, it's just the electrons moving. Now, we come back to this one. If we bring this object near this neutral object, okay, it's going to force all these electrons to move as far away as possible from this charged object. And then if I come in and touch this sphere, then what happens is those electrons still want to get further away, so it's called grounding. They jump to this object here to get away. And if I remove that object now, that these electrons have gone over, and now if I remove this object here, get rid of that, no longer touch it to that sphere, now this one is positively charged. I never touched it with the original charged object. I just grounded it. But now if I ground it again, let's just say I bring my finger over towards it again, now those electrons are going to jump back out of my finger and make that neutral again. Okay? This is induction. Induction is without contact. All right. So Coulomb's law. This is that big long electricity equation, where Fe equals K, Q1, Q2 over R squared. This is how you would figure out the electrostatic force between 2 charged objects. All right, and K is the electrostatic constant. It's on the cover of your reference tables, and it's 8.99 times 10 to the 9th newtons meters squared per coulomb squared. Okay. This is the charge on each object in coulombs. Don't leave them as elementary charges. And then this is just the distance between them. And it works the same as gravity. Okay, that big long gravitational equation. If we double a charge, it's going to double the force. If we double the distance between them, because that doubling gets squared, and it's in the denominator, it becomes 1/4 of the original force. So if we move objects further away, that force gets weaker. We bring objects closer together, that force gets stronger. If we make the charges larger, force is stronger. Charge is weaker, force is weaker. All right? Now if we move on to electric fields. Okay? So electric field strength is equal to that electrostatic force over the charge. Okay, so it's the force felt by this charged object, whatever that charge may be. And electric fields they're a vector, so they have a direction. So if we have a nice, simple, positively charged object, and we're drawing the electric fields around it, okay, there's 2 different ways we can do that. Actually, we're just going to go with one way for right now. It's always the direction that a small positive test charge would go. So if we have a small positive test charge, it's going to be repelled away. Okay? So anywhere we put that on here, it's going to be repelled away. And for these, the lines never cross. Okay? And how close they are together determines the strength. So as they're closer to the object, they are closer together. Out here, they're further apart. So closer to that positive charge means we're going to have a stronger electric field strength. Now, if we were to draw the force acting on this charged object, it's going to be repelled, but as we get closer, it's going to be a larger force. And further away would be a weaker force. And you have to draw those arrows with respect to the magnitude. If it's a negatively charged object, then it's going to be, that positive test charge would be attracted toward that negative object. Okay? And there could be an example where you have two positively charged objects. In that case, it's still going away, but because those field lines can never cross, they curve outward. If you remember doing these, you should. We drew a lot of them. Okay, might look something like that. Negatives would be the same, except the arrows would be in the opposite direction. If you had a positive, oops, that's a horrible circle, and a negative, you would see them, one being repelled from one and attracted to the other. So you would see something like this. Okay, right along those lines. Now you can have parallel plates. If you have two parallel plates, then the direction of the electric field is still the direction of positive test charge would go, and it would be repelled away from that top plate toward that bottom plate. And they are parallel. It is a uniform electric field between parallel plates. Okay? Because the electric field is constant, if this is staying the same, and our charge, whatever we put through there, is constant, that force anywhere in here is constant. It's not going to change. All right? That force anywhere inside those charge plates are not going to change. And the last thing is if potential difference. Okay? The potential difference, or voltage, is the amount of work per unit charge. So potential difference might be a potential difference between these two parallel plates here. Okay? It might be a potential difference, a voltage difference of 6 volts, let's say. So if we knew that there was a potential difference of 6 volts, and it's an electron, so the charge would be negative 1.6 times 10 to the negative 19th coulombs, we could figure out how much work it would take to move that electron to the negative side. Okay, if we had a little negative electron here, it really wants to be at the positive plate. We could figure out how much work it would take to move it down to that negative side. That's what that's telling us. That's the idea here. And don't forget that this can be work or energy. And it has a unit of joules. So a volt is really a joule per coulomb. Okay, but sometimes it's just easier and shorter to call it a volt. Not an electron volt. Electron volts are different, just a volt. And we'll talk some more about this stuff, a little bit more about this stuff, when we get into circuits, which is the next video.